That's what I'm talking about.
Wait! Okay, now, from the beginning.
It is indeed time for the talk. Hi everyone, my name is Andreas. And this talk is titled From C# to Machine Code, which is a dramatic title. Anyway, about me, my name is Andreas, as I said. My background before joining Unity is I've been in the AAA space for a long time, doing game and engine development. I've been at DICE, working with the Frostbite guys, and I've been at Insomniac Games. And if you don't know me, I'm one of those performance nutcases that maybe you've heard about. Anyway, I'm at Unity now, and I'm working with a pretty awesome game code team and our compiler team. And my job is basically to make this dream we have of performance by default a reality. So if you've looked at the other sessions here and you've seen all of the performance work we're doing and all of the stuff we're talking about at GDC, it's very much about performance, right? Why are we doing all this? Well, it's a direction Unity is going in, and it's easy to see why, right? Even now, like one of the most common reasons why people return mobile games or review things poorly is because they say it runs poorly on their devices, right? This affects developers, it affects you, it affects everyone who's consuming games, right? If you read a review about a game, people have started really to pick up on, like, well, the frame rate wasn't stable. Like, I think this was poorly optimized, something, right? And so gamers are demanding it, and developers are demanding it, and we have to deliver, both us as an engine team and you as developers. We all have to care. So with that in mind, who optimizes? If you're on a team and you're developing stuff, like who's gonna make this happen, right? And in theory, everyone should care, right? We know how important this is. This can be the difference between success and failure. Like, are people going to be impressed with your game, or are they not going to be impressed, right? So we would hope that our teams, when they're putting new assets in and they're writing key elements of your game, you would hope that performance is at the front of their minds, right? They would be thinking carefully about, well, how can I get more enemies? How can we do more animation, right? What's going to set us apart? How can we look good here? And maybe you're like, well, Andreas, I don't care about any of those things. Well, maybe you care about better battery life, right? It turns out to get better battery lives on the new generations of phones that are coming out, you actually have to use more than one core. Like running on one core, that's going to become history. What about smoother frame rate? Maybe you care about that. If you care about none of those things, like how about saving the planet? Come on, like there's got to be. So anyway, there's plenty of reasons for why performance should be at the front and center of everything that we're doing. And so we would hope that our teams would care and everyone would think about this actively. But in practice, it's people like us in this room who take time from their schedule to go to a session titled From C# to Machine Code, right? Specialists. So let me tell you a story here, like what it means to be a specialist. It's not unlike driving a manual transmission in the United States. And if you're a car enthusiast, maybe you meet some other car enthusiasts in the States, and you're talking about, oh, have you driven that road? Like, what gear were you in? And they start looking at you funny. And it turns out like less than 3% of cars sold in the United States have manual transmissions, right? It's a thing that's going out of style, and people don't care, and no one really knows how to drive one anymore. But, so you can get surprised that people are speaking the same language till you get to this point, right? And it's all a big mystery to them. And that's what it can feel like being a specialist. Anyway, this is a room full of stick drivers, right? You're here because you care, and I think that's cool. So it can be tough to be this performance specialist, like I said. And that's one of the things, and one of the big reasons why we're pushing on the tech side to make that job easier and more fun. So hopefully you've seen the announcements of the first round of tech that's coming out of Unity now that has better default performance choices. So we're talking about the job system, we've been talking about native collections, where you don't have to use garbage collected memory, and we're talking about the ECS. That's great, right? That makes the job easier for the specialist. If you saw Mike's talk just now, right? Things are set up by default so you can go in and get pretty dramatic speedups. And to sum it up, like I feel like this enables your teams and yourself to build optimizable code and content. So that's great, right? We basically removed most of the clowns at the factory. So when you get the car, it has fewer clowns in it. And so, if you paint within the lines and you follow this stuff, like you should expect better performance by default. But it leaves one big unanswered question. What happens to the actual code, the thing that actually runs on the machine, right? And that's what this talk is about. And the initiative here we're calling Burst, and it's a compiler. And so this is the second most important slide of this talk. So please see this one and the next one before you leave. The current options you have, right, when you're writing C# and you're delivering it and you're worrying about different platforms, they have some performance problems, and we know that. And I think the problem here extends beyond just what we're talking about here, Unity and doing C#. If you look at any game, any AAA game, any indie game, there's always tons of performance left on the table, right? We are, as an industry, poor at leveraging everything that the hardware can give us. And that's because we have sort of funky tools and deadlines and all kinds of things, and we get it working and we ship it, right? So I think this is true way beyond just Unity and C#. And this sort of problem of suboptimal code generation, right, a poor mapping to what the hardware actually does, is tough to fix. If you're the specialist and you're trying to fix this, what are you going to do? Like, you have thousands of files that all get compiled to some sort of suboptimal machine code, right, and it changes day to day as your team is making changes to it. Like, how are you going to fix it, right? You can only babysit the compiler so much. And another problem that we want to solve is that it's really, really difficult to make determinism a guarantee for your code base. So if you're worrying about deterministic network simulation, these sort of things, and you're trying to support more than one compiler and platform, it's a nightmare, and it's a problem that we want to fix. Here's the most important slide of this talk. What problems are we not trying to solve, right? Because this should put you in the right frame of mind. We're not going to become some language standards committee, and we're not going to sit around saying, well, we need to support esoteric hardware like the one in this fridge or whatever. Like, that's not a thing. And my least favorite thing about discussing languages and optimization, this sort of thing, right? What always happens is that someone in the back of the room raises their hand and says, well, that sounds reasonable, but what happens if there's 9 bits in a byte, right? Someone always has to be that guy, like the standards guy, the language lawyer who like kills all the joy of trying to optimize something. So, in fact, we are not trying to solve that problem, and we're going to say that, in fact, character bits are 8, and the address space is actually linear, like on every device anyone ever cares about. Pointers always have the same size, and all these things that can just throw a brick into any sort of attempt at making something reasonable and optimal. And perhaps the most important point of this talk is that we're not making a general purpose compiler, right? You should not expect to be able to use Burst to compile your database server or something completely non-Unity, right? We're making this tool for Unity and nothing else. All right, so with that said, I mentioned the hard problem of trying to ensure good code quality, right? That's a tough problem, and you've probably been there, like you're trying to find and those problems. And so there are other problems here because you're using a general purpose compiler tech to try to do your job. Right? In this space, there's tons of problems that no one really is looking to solve in a game context. One of those problems is aliasing, which we'll talk about in the talk. Vectorization is another one of them. Like, how do there are no guarantees. Like, you don't know what you're getting. It's basically hoping for the best. Another one is support for actively moving things around in memory so that you get better layout. And I mentioned determinism, right? Reasoning about this problem is like a big, messy, sticky problem. Another thing I'll get back to in the talk is controlling precision trade-offs. So those are some of the problems, and our strategy to attack these problems is kind of simple. What we want to do is we're going to take control of the compilation pipeline and move it into Unity. And we're going to teach our compiler to solve problems in this space in the way that we care about for games. And we're going to do that by bringing Unity knowledge into the compiler. And so we'll explore that in the talk, and you'll see what I mean. But first, let's review the options you have today to deliver C#, right? There's mono, of course, which we all know and love. It's one of the reasons that people get into Unity is in no small part due to mono, right? This is the primary focus of this technology as it pertains to Unity is to enable you to quickly iterate in sandbox and do things and be flexible and all that good stuff. Which is great, right? And it's a big reason probably why some of you are in this room. But if you disassemble what that JIT is doing, like you just want to go home and cry. Like it's not good code. And that's not the point of it, right? It's called scripting in Unity for a reason, even though it's a compiled language. All right, so there's also IL to CPP. And a lot of people think that, well, this is an offline compiled thing, so the focus is performance. But the focus of IL2CPP was never performance, in fact, right? The focus of IL2CPP was to enable you to deploy games on platforms that don't allow JIT code generation, so like the iPhone, for example. Right? And so, sure, it's statically compiled offline, you don't have the mono JIT, but there's still plenty of problems. And if you look at the code gen you actually get out on the other end, it's a little bit better, but there's plenty of cases where it's still not good enough. And furthermore, because you're working one additional layer away from the actual hardware with the C++ compiler in between and different C++ compilers to boot, right? It's difficult to iterate on the code quality. If you play a musical instrument, you'll probably find this analogy accurate. It's sort of like putting on gloves and then touching your instrument with some extra padding in between, right? It's hard to get the effect that you want. So those are two options that we have today, right? And so the third option we're adding is Burst. And this is our in-house compiler stack. And we want to engineer this to take advantage of those better defaults we're putting into Unity. And make no mistake, the primary focus of this compiler tech is performance. That's why we're doing this. We're not doing it to make it convenient or do whatever. Those are all nice things that we want to have. But the primary leading focus of this effort is performance. And not only that, but we want to make it a companion. Like when you're in that specialist role and you're looking to get that perf, this should be your trusted ally that you can just pull out and you can work with it in the same way you can iterate on game code and behaviors with mono. We want this to be your performance workbench. So in the big picture, you've got your game, all your code. As you may know, we're rolling out packages, right? So in the future, you'll depend on a bunch of packages that do a bunch of heavy lifting, which is great. One of those packages that we're very excited about is the ECS. And all of these modules and your own game, they're going to be producing job kernels, things that you've seen in Mike's talk and other talks, right? This is the way we're going to be writing performant code in the future. And so we've got hundreds and hundreds of these different types of workloads. They all sit on top of the job schedule and the runtime, and they're all supported by these garbage collection-free containers. And that's all backed by the Unity runtime. And so now there's this big square, you may be guessing what's going to go in there, and that's where a compiler slots in. So you can see we're taking a very deep integration approach here, right? The Burst compiler is a package, and it's deeply integrated with our jobs and the way we type them up. It's also integrated with the job scheduler, and it's integrated with the native containers. It has awareness of these things, right? And it cooperates with the Unity runtime to deliver a completely deep integrated compiler stack, right? It's not like we're taking some executable and just bolting it onto the side. Like, no, this is a Unity effort. If you know me and have followed what I've said, here's what I said 3 years ago. I said, compilers are good at performing mediocre optimizations over and over again. And here I am telling you I'm making a compiler. You must be a liar. Well, in fact, I stand by that statement. And I stand by that statement because that's what I said about a general purpose language compiler, right? Some tool that tries to solve every problem for everyone and does so while taking into account the guy that has 9 bits in a byte and every possible thing that you can ever hope to run code on, right? And this implies that you accept all of those constraints, right? You have to make all these trade-offs, and often when people ask, why can't the compiler do X, right? That's often the answer. But if you look outside of that space, if you look into specialized compilers and those sort of other transformation tools that have a much tighter bound or much tighter constraint, like a shader language, we're suddenly seeing a lot of optimizations that just make a ton of sense, right? And we hope that we get some of them in C++, but we often can't because of reasons. So when we asked ourselves the question, how can we get our C# code generation to rival the best handwritten code and the best code that comes out of the most special purpose compilers, we realized that setting constraints is what we have to do to make this a reality. And that's why we're introducing high performance C#. Right, so this is a perfect subset of C# that has some pretty tough constraints if you're used to the full language, right? We're taking away class types, we're taking away boxing, we're taking away GC allocation, and we're taking away crazy things like using exceptions for control flow, which honestly you shouldn't be doing anyway. And there's some other things in here, like you can't really access statics, and like we're really making this a very, very tight constrained subset. And we're doing that not because we like to punish people. We're doing that because this means that we can optimize it really, really hard. And because of the constraints with the language, it also means that we can actually analyze a lot of stuff offline and at runtime, right? We can safely tell you that this is going to work without race conditions and things like this. Right, so maybe if you're feeling uncomfortable at this point, well, why are you taking away the C# that I know and love? Like, it still looks like C#, it still is C#, right? So you don't need to read this entire slide, but I'm just calling out a couple of things here. Like, first of all, you can still do plenty of abstractions with structs, right? And here's one that implements an interface, which is okay because generics and interfaces play nice as long as you take care. And if you make a mistake and you happen to introduce boxing, our compiler will tell you. You've got attributes here, and you can see that some of these attributes are actually some pretty advanced abstractions that are still written in this high-performance subset of C#, right? You've seen them probably in the other talks, but like you've got things like a component data array, you have things like an entity array, and even a command buffer abstraction here that looks sort of like a class, right? But it's actually all written in this high-performance subset. And your regular straight-line code is pretty much what you'd expect. You put in methods, and they just are on structs instead of classes, and it's pretty much what you'd expect. So it's not too scary, so it is still C#, right? And we like it because it is that sandbox. And you got all of the basic types, you got structs and enums and generics and interfaces, right? And if you make a mistake and introduce boxing, the compiler will tell you. And so we're retaining all of that good stuff about iteration and safety. Like, you're not going to take down Unity by using it. You know, the most common question that we get when we talk about this is, why can't you just fix C#? Like, just make it better. Like, I wish I could, like, wave some magic wand, but like, if you think about Microsoft and other companies, they have hundreds of extremely talented engineers who have been working to try to solve this problem, right? To making garbage collection algorithms faster and all the things. But I haven't seen a garbage collection algorithm that can actually deliver hitch-free gameplay at 90 in a VR title. It's just never going to be a thing, right? Don't solve that problem because there's no solution. And that's what we're trying to do. We're trying to focus on the subset that we can guarantee you we can optimize. All right, so that's out of the way. Let's talk about how the compiler works. So currently, we compile your assemblies normally using the C# compiler, right? Which means they can run on mono or they can run on burst. And that's good when you're debugging, for example. And then in the editor, when you have burst enabled, what we do is we consume that IL that comes out of the C# compiler, which is currently opt-in. Like, you have to tag your jobs to enable this. And then we transform to LLVM IR, and we feed in a lot of metadata that we happen to know because we control the whole ecosystem. And we run LLVM's optimization suite, and we JIT that, and then we swap out the code dynamically in the editor, right? And this is your performance sandbox where you can iterate on stuff, and you can measure the performance as you're working. What the team is working on right now is fully integrating out the ahead-of-time workflow for this, right? So all of the stuff that's tagged for burst compilation is going to go into and blend together with your IL to CPP output so you can deliver a fully optimized build that has no JIT. And when I say performance sandbox, I mean it, right? We want to show you what's going on under the hood and give, you know, a performance specialist the tools he needs to do his job, or her job for that matter. And the Burst Inspector is the first one of those tools, but we're going to make even deeper integration here in the future. And so the Burst Inspector is this tool where you can look at all the kernels that are currently tagged for compilation and find them there, and pick them, and then you can iterate on the code gen, right? So you can look, okay, what if I compile this for AVX? How does it look for SSE, right? You can look at all these different hardware features and see how it transforms your code and see that it makes sense for you, right? Is that what I expected? And you can also see the .NET IL that we consumed and fed into this, right? So you can look at the input to our compiler and see if it actually lines up with your expectations. Like, why is it compiling this? I thought this was if-def out. Like, why is this here, right? It's a very, very transparent way to work. And you also get the LLVM IR, both unoptimized and optimized. So if you suspect that there's a compiler bug, like, well, you have all the tools here. It's very easy to copy these things out and just tell them, show them to us, and we can figure it out. You can also play around with the different compile options here. Like, you can enable the safety checks, which normally you should have disabled when you're profiling things, but it's convenient to see just how much they're adding in terms of overhead to your code, things like this. So again, what we're trying to do is trying to make Unity better by having a compiler, but we're also trying to make this compiler way smarter by knowing stuff about Unity. So I'll talk about 3 things here in the talk, and one of them is context-aware alias analysis. The other thing I'm going to talk about is I'm going back to the precision determinism, like what are we doing there? And we're also going to look at some research we're doing with higher level data layout changes you can make to arrays. But let's start with aliasing. So if you're not familiar with this concept, right, you may go to Wikipedia and then read in the most high-strung Wikipedia voice. In computing, aliasing describes a situation in which a data location in memory can be accessed through different symbolic names in the program, right, which means you have more than one pointer reference to a thing. As a result, aliasing makes it particularly difficult to understand, analyze, and optimize program. Emphasis mine. Okay. So let's walk through a simple example. And I use C++ here for this 5-line function, but you'd have the same problem in C# with a managed array, for example. Right? So you have two inputs coming in here, A and B. There are some blocks of floats. And I have an output block. Like I'm going to write some floats over here. Fantastic. And then I'm going to pick 8 floats from each array, and then sum them, and I'm going to write them to this output array. Right? And if you're anything like me and you like to keep up on how hardware works, you're like, wait, I know hardware can do like more than one thing at a time. There's this SIMD thing, so this looks like the perfect example, right? It's 8, which is like a perfect match for the SIMD width, so I would expect this to be really efficient. Like maybe this is in some low-level code or whatever. And you compile it using the best compiler in the market or whatever, Clang, and you get this. All right, so I'll excuse you if you don't read assembly. So in fact, I prepared some slides. Well, this is a scalar move. That's a red flag right away. Like, oh, wait, we're fetching 1 float. OK, that doesn't look like a good beginning. And then we're doing a scalar add. OK, and now it all makes sense, right? We've got scalar loads and scalar adds, and the compiler unrolled it for it 8 times. OK, why did it do that? Like, and we're scratching our heads, and we go back to the code. Oh, and we realize is aliasing, right? The compiler cannot know that your output block isn't one of the input blocks. And what if it is, right? Then you're actually mutating what you're going to be reading next. And the compiler has to be defensive and assume that that's what's going to happen, right? And what you can do in C++ and in C is you can slap this restrict keyword on a pointer. And this tells the compiler that, no, it's OK, you can break the rules. I promise, which we'll get back to, that this output array is in fact not overlapping with those input arrays. And what do we get instead? We get this. So again, I'm going to be helpful. You've got a packed load operation for memory, right? This moves 4 times as much data. So 4 floats at a time. And this add instruction is adding 4 floats independently of each other together, right? This code is 4 times as fast. So why am I boring you with all this? Like, why don't we just expose restrict to C# and you can sprinkle it everywhere and things are great, right? No, because first of all, like, I don't know how many people in this room had heard about restrict, or you know, when you look at a lot of code bases, like people don't really go through the time to put restrict in everywhere to get these sort of simple speedups. Why don't they do that? Well, remember, I had that function up, and we could reason about it, and had 8 floats and everything, and that's great, right? But really, that keyword, while it applies to the function, you're really making a promise to your compiler and your tool suite about every possible call to that function, present and future, right? You're promising the compiler that junior guy you're going to hire in 3 months, he'll totally be on board with this. Like, he's going to get this, and he'll never make a mistake, and he's not going to alias the arrays. And if he does, like, undefined behavior doesn't even start to describe what's going to happen. Right? And if you do, this is like an extension that's not even standardized, so good luck with that, right? And OK, so if that happens, like, how do you know that it happened? Well, you don't. Like, there are no tools, and we're back to like scrubbing all the object files and looking for things that look wrong, right? So it's a difficult tool to use correctly. And another serious problem with restrict is that it's not helpful if you can't get to the pointer. Right? So in a C# context, if you have a list of T or something, inside it sits a managed array that has a pointer. Like, you can't get to that pointer. Like, how are you going to put this information into that struct? Right? And in C++, you've got std vector, also contains a pointer. Like, you can't get at that pointer if you like don't fish it out and throw away the vector, right? So here's another way that this fun problem can materialize. So again, I'm using C++ here for this example, but you know, again, you'd have the same problem in C#. So bear with me. Here, I've made sort of a very simple std vector-like abstraction. So it's an integer array, right? So I have a pointer to a block of ints, and I have a count. And I have a member function here on this array abstraction to say, like, hey, go through the array and set every element to a particular value. Okay, seems straightforward. And then maybe it's you, maybe it's someone else on your team swings by and they're like, hey, let's not get all spendy here and spend 8 bytes on that count because we're never going to store more than 4 billion elements in here. So let's switch that to an int, right? And that's the only change that gets made. You're like, I guess that's reasonable. We can check that in. And then the day after, you being the performance specialist, you get this bug. Hey, this code is 4 times as slow. What? Like, what happened? Well, let's look at the disassembly. So on the left-hand side, where we had a size t, we're getting blocks of 256 bytes moved directly into cache at the speed of the machine, right? It's pumping out as fast as possible. So it takes 0.6 micros to run that for like an 8K sized array. But what's going on in this right case here, where we changed it to an int? Well, first of all, we're moving elements one by one to memory, so that seems not awesome. And there's this guy in the loop, right? This is a needless reload of the count of entries, right? So for each iteration in the loop, the compiler reloads it from memory. And in fact, this is the slowest part of the loop, right? The latency of this instruction on x64 is the slowest thing. So what is happening here is that the C++ compiler using type-based alias analysis has to assume that you have set things up so that the base pointer to your first integer actually points to the count variable. That's what it has to assume. Because someone could do that, that's what it has to assume, right? And you can see one potential fix here, which is to say, I'm going to load the count into a local variable, which then cannot possibly be aliased, because how could you have a pointer to it when it didn't exist, right? And you just use that local copy of the count, and then we're back to that optimal code gen, right? And needless to say, like, this is fine for a simple example. You can sit down and work it out like this, but how are you going to do that across your entire code base, right? And that's the real problem with the current state of the art with aliasing. Okay, so you know about the problem space. I think we're ready to play Will It Alias. If you start combining things into structs, right? I have struct foo, I have an unsigned integer, and I have a float going on in there. All right, so you're looking at some code, and these could be references, so it doesn't really matter, right? And you have 2 aliases here. Like you have a foo pointer and a float pointer. Will the compiler have to assume that they alias? Yes, because you could have a pointer to the float inside of the struct, right? And all bets are off, so we have to be defensive. All right, so you're like, well, here's this other case. I have a foo pointer and an int pointer. Clearly, they should not alias, you think. But alas, they do alias because C++ and the type-based rules they're used therein assume that unsigned int and int, because they're sort of sibling types and they have the same size, no, it's okay, they can alias. And the problem doesn't stop there, right? It's not like you can look at any sort of abstraction and just see what's in it. Quite often we abstract things further by putting things into ever deeper boxes, right? And so here I put this foo struct twice into a bar. And now we come dragging with that int pointer, you know? And you're looking at this code at face value, like, well, I don't see an int in there, so this should be fine. But in fact, it's aliased anyway, because you could have a pointer to deep inside of that hierarchy, right? And this just points out how difficult this can be to just analyze at face value. All right, so to wrap up the problem statement here, what actually is the problem with aliasing is not that the code is incorrect, right? It's that it prevents the compiler from using SIMD instructions. As you saw in one of the simple examples here, it's often a 4x performance loss. That's not only it, but I'm not going to bore you with super low-level architecture details in this, but if you're really interested, you can go back to my talks from a couple of years ago and look into more into why that's true. But we also saw that reload of a variable in the inner loop, right? And quite often, those are going to be the silent performance killers. They really, really slow down your loops. And so this is a problem because compilers working without context cannot possibly solve this, right? A C++ compiler or a C# compiler can't reason about every possible call you can make to a thing and then make a global choice, right? So we need to allow the compiler to break the rules, and that's the current state of the art. Here's what we're trying to do. We're trying to put that context into the compiler. And we can do that because we know much more, right? Each job that you compile, we know cannot get any sources of pointers from anywhere else besides from the inputs to your jobs, right? And so all the native arrays and component data streams and everything you're setting up, we actually guarantee when we schedule those jobs that those things cannot have aliases. They're guaranteed to be unique. And because we own the compiler, we're telling the compiler, hey, this is true. So in fact, it is as if a performance specialist had visited every part of the code and making sure that those annotations were there automatically. So we're not actually arrived at a fully perfect solution here. Like there's some pitfalls, which, if you want to be bored to tears, I can talk to you about. But what we're seeing, even with the very first sort of scratching the surface implementation here, is that most loops have a much better chance to auto-vectorize. And we get out of those needless reloads of data. And the gravy is that it costs nothing to maintain for you when you're trying to get perf across your systems. So just to go back to that initial example I had where we're adding 8 floats, right? Here's the same sort of idea expressed as a C# job. So again, I have 2 input arrays that are read-only, and I have an output array that I'm writing to. And I'm doing the same thing, right? I'm pulling out 8 floats and I'm writing them. There are no annotations, there's no crazy markup, it's just the way you write it in the C# job system. And it generates SIMD code by default. Right? You don't have to do anything. So that's cool, and that's where we're at today, and we can do better for more complicated use cases when you start copying these things around and moving them or whatever. And we think we have a really good shot at doing that. So I also mentioned precision control, right? And so the reason we think precision control is important is that quite often in a lot of code segments you can get a good speed up if you don't need that last bit of precision. To compute things with lower precision and lower accuracy, that has to be a decision that you make as the author, because it's context dependent. If you have visual effects in the far distance, like it's a smokestack and it's going to be 15 pixels high, like who actually cares if it was computed using doubles or halves? Like it's going to look the same. So you just want that to go fast. But maybe you have another case with it's also a visual effect, but it's the one game-defining thing and it has to look good at 4K. You don't want that stuff wobbling. Maybe it's your terrain pathfinding code that, if you take away too much precision, it actually starts dividing by 0 and generating paths that, don't make sense. Or maybe it's, some completely custom game thing. And the point is, like, only you know, right? A general purpose compiler or system can't make those trade-offs for you. So if you're trying to do this today, and this is very difficult to do in C#, but in C and C++ you can sort of do it, but you have very sort of clumsy controls. So if you need to work with half-precision data, which if you're not familiar is just a 16-bit float, right? And so it's got a very small range, but most hardware nowadays comes with dedicated support for half, right? So you can do twice the work with the same bandwidth. That's cool, and I can think of hundreds of cases where you want to use that in the game. But if you need to do this today, you need intrinsics, and you need to do all the things like for a specific platform and really downcode it. So a lot of people don't. And even if you're just trying to make floating point operations be more flexible, say like, I don't really care about this particular thing, you can fold the expressions here, and you can just give the compiler more leeway. The only tool you have really is just like treat the whole body when you have a headache, right? So there's this fast math option, and you sort of do it per object file, and it's kind of messy. And it's really hard to ensure that the compilers are doing what you hope they're doing when you try to give them this license, right? So I'm talking about things like instead of dividing, you want to multiply with the reciprocal, right? And the reason a compiler can't just do that is because the IEEE rounding rules and these sort of things will not be exactly the same. So you can lose a couple of bits of precision, 1 ULP or something like this. But again, you know as the author that that's okay or not okay, right? But the compiler can never know that. And square roots and other trig functions are good examples of where you want to just reduce the precision and just get away with faster execution. So tied to this and related, but orthogonal, is determinism. Right? And so if you're not familiar with this concept, right, a lot of network models send just inputs and then rely on everyone to compute the same frame. Right? And it's a sort of compression, right? Instead of sending hundreds of thousands of units around, you're just sending the inputs from all the players, which are tiny, and then it works itself out. But it's as soon as you have something non-deterministic going on, everyone's going to desync, right? And if you talk to battle-scarred RTS developers at GDC, they will tell you endless stories about how all the fun that was. Right? So what needs to happen is everyone needs to compute the same bitwise results. for all the computation that goes on, need to do the same thing, right? And it's important to realize that this is orthogonal to precision. As long as they compute the same thing, it doesn't matter if they used low precision to do so, right? So it's not necessarily true that determinism has to mean highest possible precision. So if you're doing this with floating point math and you're trying to target more than one compiler or platform, it is very, very difficult. Because compilers reordering things or even the slightest change to something can mean that you differ by a couple of ULPs and then things start to slowly diverge, right? And your players hate you and I don't know what happens next. So you can fix this by using integer math. For sure, you can use fixed point and those things are always going to be deterministic, but like who's going to rewrite all of their stuff to use integer math, right? Or maybe you have a game that's not an RTS and you want to sort of target that space. That's a lot of code to rewrite to make sure it's deterministic. And it seems to us that no one's really interested in solving this problem, right? You don't see a lot of discussion on the Clang mailing lists or language extensions to solve this problem. So where we want to go with these two areas, like precision and determinism, is to give you control per job, or maybe per project or per module, whatever makes sense. We haven't figured that out yet. We want to expose these attributes and expose that they're orthogonal so you can get to make the choice. So to go back to that RTS example, right, I'm going to try to make a case for all of those 4 settings. Right, so a bane of my existence is that in every game I've ever worked on, basically, some junior programmer makes a bird system. And it spawns a bunch of pigeons, and they all fly around in paths, and it takes 5 milliseconds, and I just cry into my console, right? And it's just like, why are these birds here? If I had a really quick way of saying, like, wait, these don't affect the game simulation, and like they're ALU bound, not that they would be because they're going to be cache miss bound, but let's say they were, it would be really nice for me to just say, like, okay, reduce the precision here, like make them slightly cheaper. Maybe that's good enough, right? On the other hand, in an RTS, maybe you have a bunch of catapults, right? So the player needs to aim them, and long distances, you need pretty good precision, but you also need them to be bitwise exact, right? Because when you let go of that fire button, everyone has to do exactly the same thing, or the simulation is going to desync. But on the other hand, you have units. Maybe you have hundreds of thousands or tens of thousands, right? And their pathfinding is going to be quite a bit of CPU work. Now, it would make sense to compute all that with lower precision, because how much do you really care about this individual guy and the path he took? Like, no, but what you do care about is that he's on the same position on every machine, even though we're computing his pathfinding with low results. And, you can make the case for like fancy effects or something that don't affect the simulation, but you still want to use good precision for. So you can make all of these different cases. So we have some stuff here, sort of researchy stuff to figure out before we can deliver all this. For example, if you need a math library, you can't just use the FPU's basic sign function because it's going to differ on different platforms. You can't call out to the math library because it's going to be different on different platforms, right? So we have to basically internalize all of that to be able to give you guys the guarantees that this is not going to change. And so there are options here. There's a couple of libraries called Sleef and others that can also simplify things like sine and cosine. So we're looking at those. And what we have to figure out is how do we guarantee determinism, and what's the test matrix look like? What are the test cases? So if you have feedback there, just let us know on the forums. But we think that we have a pretty good plan for how to set up sort of this testing framework. We also are not sure what the performance hit is going to be. We think it's going to be reasonable, but it's definitely going to be slower to run deterministic code than fast code, right? That's accepted. But we don't exactly know how much the hit is going to be. So I'm sure there's going to be fun out-of-spec things and hardware bugs we're going to find. All right, so the final thing I want to talk about in this talk is some of the future research and what really the promise of this burst technology is. So I've mentioned SIMD a couple of times in this talk, and it really is important. Like if you haven't done SIMD or like you're just peripherally aware of it, trust me when I say that this is how you get the most out of a CPU today. And it's not only computation doing more than one thing at a time, it's leveraging the hardware resources that you have, like the caches and the bandwidth. Like all of these buses are 128 bits wide, and if you're doing a 32-bit load, you're throwing away 75% of the cache bandwidth, right? And SIMD is the only real way you have to use all that hardware. But you have to lay out your data correctly to do this. And I'm going to try to give you a 2-slide introduction to SIMD so I can set up the next section of the talk, right? So how a computer works is it does things in sequence. So we're going to add two values, let's say they're floats, B and C, right? And we have A. And if these things are all in memory, here's what has to happen, right? We have to load B from memory. We have to load C from memory, because how else are we going to do it? And we need to add them, and we need to store the result back to memory, right? Just how a computer works. Do these things. Great. All right, the only thing you have to understand about SIMD in that example is that SIMD simply makes them wider, right? Instead of loading B, we load B0, B1, B2, B3. They're completely independent Bs. It's as if you had done that thing 4 times, right? Same thing with C. We're loading 4 completely independent C values. And then when we're summing them, it's still a single instruction that sums them, but we're doing 4 completely different sums, independent ones, like if you've done the same thing 4 times. And when we're storing things, we're storing not 1 value, but we're storing 4. But the thing is, they're consecutive in memory. And so that's the only thing you need to know about SIMD, really. And so the constraints then are, if you look at the step here, we're going to load B0, B1, B2, and B3. Great. Right? That's not the complicated part. The complicated part is what we have to do as performance specialists before we get to that point, which is we have to make sure that all the data is already in memory in that form, right? Because the workarounds, if they're not, are usually often not great. You have to swizzle things around, and you have to waste a bunch of infrastructure costs to actually get to the data. So it's worthwhile calling out that if you have basic arrays of primitives, like you have distances or something that's homogeneous in nature, you already have your data in that format, so you don't have to do anything. But the real confusion and like the tough, well, I should point out that that's true as long as you don't do anything crazy between your inter-elements, which would require slightly different algorithms. But the real confusion, usually, people get arrays when you talk about SIMD, but then when you start thinking about structs and abstractions you make, it becomes much more difficult. So why is that? Well, as programmers, we tend to think of things and give them identity, right? And I blame sort of Pascal and C and Ada and every language ever invented for the last 50 years for this, right? Because we tend to think of a thing's identity as a pointer or reference to it, right? A pointer to the first byte in the struct or a reference to it. Like we tend to think of that as the thing, right? And so we conflate this concept of what the abstraction is and how it's laid out in memory. And the thing is, we're trained to do this, right? It's sort of like a comfort food for programmers. It's like, oh, now I know what you're talking about. You have a pointer to the first byte. And so when we make an instance, by grouping things together, not only are we sort of satisfying that human behavior of abstracting things by naming groups of things, right? Because humans are excellent at doing that. It's one of the few things that, I guess, allow us to function in the real world, right? I don't refer to my car as, oh, that's that pile of mechanical parts, one of which is the steering wheel, and like I say it's my car, right? I name the thing. But that doesn't mean that, people who make the car have to think like that. So it's really unfortunate that this connection between our brains working in a particular way and us picking memory layout has this performance ramification. Because what happens when we do this, like I've called a thing here, I have some grouping of 2 things, right? I have a floating point 3 position, and I have hit points. That's great. Like maybe it's an exploding barrel. That would make it funnier, but I can't edit the slides now. And we have an array of these that we're going to do some work on. Like let's blow up all the barrels. Well, because we abstracted things this way and grouped them together in this way, here's how they actually lay out in memory. Our comfort food logical instance is this box here, right? You got your X and your Y and your C, and you get your hit points. And it's important to realize at this point that these are heterogeneous types. They're different, like there's 3 floats and an int, right? And these all go in one long stream in the memory, and that's what you get with an array, right? But remember what we said about SIMD. In order to actually work with SIMD on this array, right, you're going to load 4 things. So when was the last time you wanted to do the same thing to X, Y, and Z, or floats, and hit points, which is an int, right? The only case I can think of is like setting them to 0. Like that maybe is not the most common thing that you do, right? But that's basically what we've crippled the hardware to be able to do with this layout. And still, it's the default, and it's what we do, and it just shows that those abstractions from 50 years ago are sort of getting in the way of what hardware does today. And this is called AOS, Array of Structures. So on GPUs and in high-performance programming, you can do different things, right? So if you say, well, what's the optimal layout for the hardware? Well, if you tile it around and you have the same abstraction in your head, but you don't actually use that struct, you use something else. You have increasing addresses, and you take your logical instances and you split them into a number of different streams, right? 4 in this case, right? Now I have put all my x's in one array, I put all my y's in one array, I have all my z values in one array, and I have all my hit points in one array. Two things happen. One, most programmers freak out, because now you can't use a reference or a pointer to a thing anymore. Like, our logical instance is purely a thing of our mind, like it doesn't look like that in memory anymore, and that can be confusing, right? And it's this awkward step that you have to accept. But the other beautiful thing that happens is that if you look across any one of these streams in memory, you'll find like data. You'll find x coordinates or hit points, right? Which means that this is now super amenable to SIMD, right? You can load 4 hit points or 4 x values, right? For example, let's say that you're doing a 2D projection and you don't care about the y value. You're not even going to touch that stream, right? And that makes for very trivially parallelizable SIMD. So I mentioned the raw SOA, but you can also do a hybrid of these because the traditional SOA layout has some problems, right? You need all of these massive arrays or small arrays. And anyway, you have a bunch of arrays. And that's fine for a handful, but if you start getting up into 8 or so, then you're really starting to push the hardware and the cache bandwidth on the hardware because the cache hardware only has so many prefetching streams. So what you can do instead is you can tile this around and basically store it in one long stream that's interleaved, and that's called AOSOA, or chunked or striped layout. You'll see different names for it. So again, we have increasing addresses in memory, and what we do in our single stream is we basically interleave. So we go X, Y, Z, and then hit points. All right, X, Y, Z, hit points for the second guy, third guy, and fourth guy. And these are so small that I couldn't really put in the boxes for a logical instance, but it's very similar to the SOA case, right? Our logical instance is split into 4 different places in RAM. And then we start over with a new batch, right? So you can see it's like you took that SOA layout and you basically swizzled it together by forming these small colonies. All right, so I've bored you to tears with all this layout stuff. Like, why am I doing this? It's set up to make you understand how important good memory layout is for performance. And you've seen the other talks here at GDC probably about the ECS and those sort of things. And the ECS honestly gets a lot of the performance just from the better defaults for memory layouts. Things are already packed in arrays. Like, this is the next step. What we want to do is be able to say, for this array, actually lay it out in SOA form, right? Or this chunked SOA form. Which means that things are now scattered inside of that array. It still looks like an array to you, so if you read from it, we'll actually go gather all those pieces and put them back in a struct for you. If you write to it, we'll scatter it out. So that sounds like we just made it slower, but you forget that we have our own compiler. So what we can now do is we can teach the compiler to say, oh, SOA arrays? Yeah, they work like this. Here's the layout, right? And all of the strides and all the loads it computes now when it's trying to auto-vectorize will be embarrassingly simple to vectorize. So let me show you in practice what that looks like. Here's some sort of very simple culling job, right? I have a sphere, and I have an array of spheres. And those are my 2 inputs of this job. And the purpose of it is to see, does this input sphere intersect any of the spheres in the array, right? Very common sort of test all the things problem. And in my head, I'm thinking of a sphere like this. It's got X, Y, and Z, and it's got a radius, which I don't know how you think about spheres, but that's how I think about them. And then the loop that we're going to do here is we're going to loop through all of the spheres and intersect them one by one, like I'm writing scalar code here. Like, this is not some magic. It's not SIMD or anything. And we're testing each one and keeping track of if we saw an intersection. And the intersect routine is pretty much what you'd expect. Here's one way to write it. We subtract the positions, and we add the radii, and then we compare, like, are the positions closer squared than the sum of the radii squared, right? Sort of like what you'd find on in any textbook. So that previous example will generate scalar code, even today with burst. And we're hoping to make that not true at some point, but like, it's going to be crippled by that memory layout, right? Remember, if we want to run wide on this, we now have a layout in memory that's XYZ radius, XYZ radius, right? That's really awkward to work with. So with this one line change in the prototype that we've made, we're simply saying that, oh, by the way, this is a native array SOA, and that's the only change that it needs to happen. And we generate this code. So this is full-on SIMD all the way through, like you would handwrite with intrinsics. and it warms my heart. And this is especially interesting for performance specialists. I mean, I would love to have had a tool like this doing AAA optimizations over the years, right? Because normally what has to happen for this to work is not only do you have to go touch your containers and your arrays to declare that these are SOA, you also have to go touch every place that you're accessing them to make this transformation for gathering and scattering, right? And that's a ton of busy work. So in practice, you just have to pick the most important ones and hope that you guess right and fix just those. But with this sort of tooling, you can do it on a much, much bigger level. So that's where we're hoping to go with memory layout. All right, so in conclusion, we're trying to make this compiler smarter by teaching it about Unity. We want to teach it about our jobs, our scheduling, how our containers work, how memory layouts work, and we can do that because it's our compiler. And we're only going to be compiling Unity code. Like, you won't find a download of this that you can compile database servers with. And you've seen examples here in this talk and other talks about high-performance C#, which is this optimizable subset that enables all of this to work. So that's it for my prepared talk, and I think we have a little time for questions.
Thanks for the talk. So you mentioned this burst compiler is coming out in 2018.2, but that's also based on the new HPC#. So does that how is the transformation gonna happen? Is there gonna be a transition period, like opt-in for a while? Are there parts that are gonna be you just can't translate to HPC# certain parts? How does that work?
Okay, so the question is, because this is coming out in 2018.2, we're not going to rewrite our code, all of our code in HPC# by then, so what's the plan there? Is that fair? Well, the compiler is not changing. This is the language subset it is going to compile, right? And this is the direction we're on now with the performance initiative at Unity, right? But we have plenty of features that are not ready to be moved into this ecosystem yet, so it's going to take a little while, right? But this, for us, embodies the future. This is where we want to go. So I can't give you a perfect date or a timeline, right? But it certainly will be production ready this summer. So you can start moving your game code and other things onto this. And if you write in the subset, you can actually use this compiler. So it's just a matter of what features do we bring over first.
So you can start translating parts of it into this subset or using this specific patterns, and then the compiler will take advantage of it.
Yeah, and you can even do things like, if you have a mostly data-oriented system, but you have a few tendrils reaching out into the object-oriented world, like the game object stuff, but you can't access from jobs, right? You can still do that thing on the main thread in the regular Unity space, and then set up the data, and then move parts of your work over to this space and still get most of the benefit. So yeah, that's available. This summer it'll be available for release, is what we hope, so you can actually ship games like that. Cool. Other questions?
If you manually stride your structures today, will Burst vectorize it for you?
It's hit and miss. It's a good question. So the question is, if you were to do that SOA transformation yourself, right, you would just say, well, I'm going to write just, in C#, in unsafe context, you can use the fixed keyword, to make small blocks. Right, so I could have done that. I could have said fixed float 4 or whatever, and I could have done it all the way, and we can have an array of those. And the answer is it depends. So LLVM's auto-vectorizer is not particularly great for those types of things. Sometimes it'll work, sometimes it doesn't work. And when it doesn't work, it's very frustrating because you can find that, you have for this particular example, I was actually trying to get it to auto-vectorize using exactly that pattern, right? And what I found was, if you wrote it the way I wrote it here, it doesn't work. But if you take if you take out the loop that loops over those 4 things in the inner loop and you split that into separate function, you get vector code, right? And it's super brittle. And we think that the only way to get that to work is to basically force feed that information to the compiler.
So one question I have about how the structs are laid out in memory is, what about empty structs that are just tags, as one of the previous developers discussed? Is there an empty base class optimization for that, or is it just a byte or something?
Yeah, so the question is, what about structs that are empty, right? Are we going to do anything to magically optimize those away? And I think the answer is twofold. In general, we're not going to do that, but in the special case of marker types in the ECS, we're definitely going to do that, right? Because as we're developing these demos and sort of trying to show you guys what the best practices should be, we're finding that we have a lot of uses for those, and it's kind of dumb to reserve a byte that you're never going to put anything in, right? So yes, in the ECS, that's definitely on the roadmap. That's what we want to do, and we want to be able to have basically free tags. That all we need to know is that it's there, because it doesn't have any data, we don't need to store it, so yes. One up front, I think.
Will it be possible to fill a compute buffer with those like optimized arrays? Because when I saw that, I was like, yes, if I could just like point to that directly and wouldn't have to like build my own array and then send that over to a compute buffer, that would be super nice.
Right. So to sum it up, like you're asking, can I basically put one of those arrays in a compute buffer and then just kick a compute job on it? Today you can't. Well, you can make one and then copy it, right? Yeah. But it is not built in at this point. But we're definitely exploring that option. And we think that there are certain cases where it can make sense, especially on PC machines, where you typically can have a little more GPU wiggle room compared to like a phone or a console, right? It makes a lot of sense to be able to target a subset of the compute work there, but that's research. Like I can't promise when that's coming, but you know, just like you pointed out, it's not a very difficult leap to make. So we're definitely thinking about that.
Thanks.
All right, one more. No? All right, then we're all good. Thank you.